Hello everyone. Let us continue our discussion on reinforced concrete design. We are in week 2 and this is our 5th lecture. So we have learned how to design singly reinforced and doubly reinforced section. As you can see on your screen, this is a typical singly reinforced section that we have already solved, and we located the neutral axis from the topmost fiber, and then we also evaluated the moment of resistance, that is the sectional capacity. Then we also worked out the same parameters for doubly reinforced section. Now, if you look at this singly reinforced section, our assumption says that the concrete in this region below neutral axis, that is the tension zone, is not effective. In this region, the only contribution we get is actually from the steel, which is here. Now the question is, will there be any difference in the moment of resistance if by chance we reduce this cross section in the tension zone? And then from this what we get is a new cross section where we have the upper part of the neutral axis remain as it is. The only modification is that we have a small portion of the concrete in the tension zone that is actually holding this steel. Of course, we have to satisfy the requirement of clear cover or effective cover and the distance between bars. That we are not for the time being worried of. If we can manage, then the question that we are trying to investigate whether we can reduce these concrete, and then if so, what the section we get and how we can design that section. So the section that we get here is what is called a T-beam. As you can see the structure, so it is just like a T, so we call it T-beam. Now the question is, in case of slabs with beams, for example, if you have a slab here, then this load from the slab is actually transferred to the beam. So we have a beam here. So this is a beam. And then we have a slab here. Now obviously when we cast this slab along with this beam, obviously both of them bend together, and therefore a part of the slab also takes part in bending. If say this is the part, then again we get a similar type of section as we have it here, or a better portion is here. So effectively what we have a flange, and then we have a web which actually holds the tensile steel. Even before going into the details of that, what we can conclude that we have less amount of concrete in the compression zone. Obviously this is more economical. Not only that, we can also sense that because of this extra width, the flange we have in the compression zone, the compressive force is very high, and that also offers additional moment of resistance, leading to an economic use of material for the given demand. Now, in IS 456, we have the same clause 38.1 that also talks about this kind of section. If we have a T section, or we'll have other type of section, for example, if this slab which is supporting a beam is at the corner, then what we have this type of arrangement, then we have a beam here and a part of the slab actually contributes. So we have L-shaped section. So these are the different type of section we encounter, and in this lecture we'll see how we can address the sectional capacity if we have this kind of geometry. Now, before we move into the details, let us first quickly look into one important aspect of this type of sections where there is a variation in geometry. So if we have a flange here and a beam there, and if they are moving separately, then obviously the strain diagram what we have here, this case they are not acting together, so this is not a flanged section. On the other hand, if we have a flange and then we have the reinforcement in such a way that after casting this entire section works as a monolithic one and they together participate in bending, then we have this strain diagram. Obviously, we are about to take this type of sections where the flange and web are monolithic. Now, before we move into the details of how to calculate the moment of resistance for this section, let us quickly go through the different kinds of shapes that we encounter when we talked about flange section. It may be a T section, as I have already explained. It may be L section. Sometimes, to accommodate additional, the amount of steel that we have additional space here. So it is a kind of I-beam with flange at the top and flange at the bottom. The bottom flange effectively houses the steel, satisfying the effective cover here and the distance between the rivers. Sometimes we have inverted T and L sections. In case of foundations also, we can have slab which is supporting some beams. So this kind of sections we very often encounter. And here also you can see this slab here is taking part in bending, and a part of the slab will take part in bending with this beam. Similarly, in case of this middle one, obviously a part of the slab will take part in bending along with this beam. So our task is to find out the sectional capacity if we have this type of geometry. And then obviously first thing we have to work out is the effective flange width. For example, if we consider this beam, not the entire length of the slab will take part in bending with this beam, but this part of the slab will take part. So this is the width of the flange, and then we first have to find out the width of the flange, and for that we have a very specific clause in IS 456, that is 23.1.2. Okay, so now let us see how we can first find out the effective width of the flange, and then we will see how we can move further to find out the moment of resistance. Let us first talk about the isolated flange section, where we have this small b is the total width, and then bf is the effective width. There may be a situation where b is equal to bf, then obviously the total width is taking part in bending, but normally bf is less than this total b. And then for this geometry we have capital df, that is the total depth of the flange. Then small d, this is the effective depth. As you can recall from our previous discussion, it is the distance of the steel in the tensile zone from the extreme compressive fiber. So that is the definition of effective depth, that we can find out from the total depth minus the effective cover is the effective depth. Then for this section we also have this BW, which is the width of the web. Now this BF, as per codal provisions, is minimum of these two quantities for isolated flange section. So if we have a bigger B, obviously the whole B will not take part in bending. So we have to find out the minimum of these two. The first one is, here we have L0. L0 is the effective length of the beam. So L0 in the numerator, and in the denominator we have L0 by B plus 4 whole plus BW, and B, whichever is minimum, that we have to consider the effective flange width. Now, when we talk about a isolated beam supported over wall, as you can see, the effective length of the beam is the distance between the center line. Depending upon the support condition and the continuity of the beam, this L effective may change. As you can see here, we have a continuous beam, and the bending moment diagram, typical bending moment diagram you can see here. Ideally speaking, this effective length for a continuous beam having this hogging and sagging bending moment is the distance between the zero moment point, that is the point of contraflexion. So this is the L0, which is 0.7 of L effective. L effective is again the distance between the center line of the supports. So we can now figure out what is the L effective or L naught, and then once we find out L naught, then we can find out the minimum of these two, and then that will give us the effective flange width. In case of L section, we have these two conditions, and minimum of these two will give us the effective flange width. Now, these are isolated flange sections. Let us see a different configuration. Here what we have is a slab is supported over these beams. So we have, these are the beams, center line of the beams. And then if we take a cross section and then see the cross section, what we get is here, say this is XX. This section is shown here. So this is the section. And then you can see we have the distance B1 between two supports, that is the clear distance, and B web. Then ideally speaking, this B1 and then B2, which is the clear distance of the next span, and then B3, B4, this may be equal, may not be equal. For the time being, if we assume that they are equal, then for this T section, we first find out B effective, which is the minimum of these two. So for this section, again, we have to find out what is L0 or L0. Then we know BW and DF. Then we can find out minimum of these two quantities, and that will give us the effective width of the flange section. Similarly, for L section, we can use this expression and find out what is the effective width. So now from this geometry, we can figure out what is the effective width of the section. Let us take a quick example. So for this T-beam, let us calculate the effective width. The simply supported beam spans 8 meter. That is the effective span. And then because it is simply supported, so L0 is equal to L effective. So we find out the minimum of these two conditions. B is given, that is 2000 millimeter. And then we find out L0 by B plus 4 plus BW, which is 1400 millimeter. So minimum of these two is 1400. So our B effective in this case is 1400 millimeter. Now, if we extend that example for a continuous beam with effective span 30 meter, then we have these dimensions given. Then for this beam, again, L0 is actually 0.7 times the effective span, which is 30, divided by 6 plus BW, which is 400 here, plus 6 times 100, that is capital DF. Now, this is 4,500 millimeter, and then the other condition, which is here, gives us 2,650 millimeter. So the minimum of these two is the effective flange width, which is 2,650 millimeter. Now with that background, let us see how we can find out the location of neutral axis and the moment of resistance. For that, let us first consider this flange section, which is a T section here. Now, there can be two different situations. The first one is where we have the neutral axis as shown, but this neutral axis, the location of the neutral axis can be within flange or can be in web. So we'll take both the cases one by one. First, what we do, we find out for this effective depth, what is the limiting value of XU. That, depending upon the type of steel we have, we can figure out from this expression. Now, if we think of a under-reinforced section, that is neutral axis XU is less than equal to DF, that is the flange. So our neutral axis is at most, it is at this level. Then what happens? Then you can easily sense that this XU is less than XU limit, and therefore we have this under-reinforced section. If that is the case, we can analyze this section as good as a singly reinforced section, because below the neutral axis, this region, even if the concrete is there, we do not consider. So effectively, we have the compression zone of concrete, which is here above the neutral axis, and then we have the steel here in the tensile zone, and we can easily find out what is the effective value of moment of resistance. For that, first what we do, we find out the position of the neutral axis. For that, we equate C with T, and this expression we are familiar with. It comes from the singly reinforced beam design, and we can find out XU. It has to be less than DF or this XU limit, because then only we can apply this theory. Otherwise, a part of the wave we have to consider that we will take next. Now, the moment we have a under reinforced section, then we can find out moment of resistance using the compressive force. So, the moment of resistance is compressive force C times the lever arm. Then again, this is the same expression we have for singly reinforced beam. We can also find out the same moment of resistance from the tensile force. So, for that, this is the expression, and both of them will give us the moment of resistance for this section. So, the point to be noted here, if the neutral axis lies within the flange, then this flange section behaves like a rectangular section. There is no difference. Now, let us see if we have a different situation. In this case, we have the neutral axis somewhere here. Clearly, we have a part of the wave which is also taking part in this development of compressive force. So, the condition is XU is greater than TF. Now, we have different situations that may arise. Recall what is this 3/7 XU? It is actually this location where it first starts from parabolic to purely plastic. That is the idealized section. So, this distance is 3/7 XU that we derived long back during our discussion on singly reinforced design. Right. This we derived. You refer the old class notes, you'll get it. So, now if the DF is less than DF, that means depth of flange is less than this, that means it is purely in this region where we have a rectangular section of the stress block is acting as the compressive force over this flange part, right? So, under this condition, let us see how we can find out the moment of resistance. So, simply what we do, we split this section, flange section, into two parts. The first part is very slick beam with width of BW, and we have the tensile steel AST1 that is as good as a rectangular section. And for this section, we can easily calculate what is C1, we can calculate what is T1, and we also can calculate what is lever arm 1. Plus, we have a situation where we have the part of the flange which is actually taking part in the compression, leaving the originally considered width of this section which is here. Then what we have for this section, we have this C2 is the compressive force. To balance that C2, we have to develop some T2. For that, we have this AS T2 as the steel requirement. Now, in this stress block, we can identify the stress values. Here it is 0.45 FCK, you are familiar with, and we can easily calculate this location Y1 of C1, and then the steel at the tensile phase will have the stress value of 0.87 FY. So, if we multiply AST1 with this stress value, we will get T1. Similarly, in case of the second beam that we have here, the stress in steel is again 0.87 FY. The extreme compressive fiber will have 0.45 FCK, and for that we can find out what is C2 and the location of this force. That we'll do in a minute. So, for the location of the neutral axis, again what we have to do, we have to balance C with T, but remember in case of C, we have C1 plus C2 as I have already explained here. So, we have C1 here and then C2 here. So, C1 here and then C2 here. That is the total C. And then that is balancing the total tensile force T. So if we write down the expression, we have 0.36 FCK times XU times B in case of rectangular section. Now because the first section has effective width of BW here, so that is the same value we put it here. That's the first part, that is C1. For C2 again, we follow the same principle. We find out the effective area and the stress level, and with the help of these two, we can find out the value of C2. On the right hand side, we have 0.87 Fy times the amount of steel that we provide. This is effectively AST1 plus AST2, right? And we have this for this condition. Now we find out what is XU, and that must be greater than DF. If not, then we have to revisit the problem, because that's how we have calculated the location of the neutral axis. Now once we ensure that XU is greater than DF, that means the neutral axis is within the flange, then we can find out the moment of resistance for this section. So for that we have MR1 plus MR2. MR1 coming from C1 times LA1, that is the first slick beam we have here. Then for that we have MR1, and for the second one we have C2 times LA2, which is here. So this is our LA2, and if we can find out what is C2, then we can find out the second part of the moment of resistance. Both of them we can easily calculate. We know how to calculate both of them, the value of the force times the lever arm. So these are the two components that will together give us the moment of resistance of the section. Now if we wish to find out the same moment of resistance from the tension, then first what we have to find out the combined location of this C1 and C2. So we have to find out the effective C for this section, which may be somewhere here, we don't know, and then the depth of this C from the top fiber, because then only we can find out this distance. So this is the lever arm, right? That lever arm, when we multiply with the tensile force, will give us basically the moment of resistance if we evaluate the same based on this tensile force. And that's what we do here. For that, first we find out the CG. What we get here is Y bar, and that is C1 times Y1 plus C2 times Y2 divided by C1 plus C2. Y1 we get it from the singly reinforced section, which is 0.42 times XU, and Y2, as our assumption says, it is the middle of the flange section. So this is the location. Obviously it is DF by 2. Now using these two values, we can find out this Y bar, and D, that is the effective depth minus Y bar, is effectively the lever arm, right? So that lever arm what we use here. So moment of resistance is T, that is the tensile force, which is 0.87 Fy times AST times the lever arm, which is D minus Y prime. But again, we always prefer to evaluate moment of resistance based on the compressive force. That's what we'll follow. Otherwise, we can also evaluate the same using this expression. Now we have another case where XU is greater than DF and DF is greater than 3/7 XU. That means this is 3/7 XU. So we have the bottom of the flange, which is somewhere here. That means when we calculate the area of the stress block here, we will have a rectangular part and then another part because of this parabolic shape here. Then for the web portion, we have this segment. Now for that, what we do again, we follow the same concept. We first split this into two different halves. So what we have in the first part is exactly same what we did earlier. For the second part, we have this B which is somewhere here, and then obviously we have this curved part here. Now that we simplify using this rectangular, equivalent rectangular part, and then once we find out this, we can easily evaluate what is C2 and what is Y2. Y2 will be half the distance of this. Okay. So what is YF? It is given here. Now this is a expression that we can readily use if we have this curved part here, and for that effective rectangular section depth YF is given by 0.15 XU plus 0.65 DF. So what we do, we calculate YF, and then based on that value of YF, we can now evaluate the moment of resistance. So again, what we do, we first check the location of the neutral axis. For that, we balance C with T, and as usual, there are C1 and C2 in C, and effectively we balance it with T, and then we figure out what is the XU. It must be greater than DF, otherwise we have to revisit the problem. And for this case, we also have DF is greater than 3/7 XU. Then our task is to find out moment of resistance, which is again sum of MR1 and MR2. For MR1, we already know C1, that is here, times the lever arm, which is again coming from the singly reinforced section. C2, we have, this is the C2, we have the stress here, times this is the area, YF times this is the width, that is the area, and then for that we have the lever arm here. So we can find out what is the effective sectional capacity. And we can repeat the same exercise from tension side, and for that again we have to find out Y bar and then follow the same steps which I have already explained. But as I said, we prefer to have this moment of resistance evaluated from the compression side. Okay, so with that background, let us first take an example. So in this example, as you can see, our task is to evaluate the moment of resistance. What are the given parameters? We have B is 2000. We have effective depth of the flange beam is 700 millimeter. Then DF is 150 millimeter. It is made of M25 concrete and Fe 500 steel. And in the tension zone, we have 6 bars of 32.5. Now, the first thing, it is a simply supported beam with L effective as 9 meter. So for simply supported beam, L0 is equal to L effective. Then we can find out the minimum of these two, and effectively what we get, the effective width of this flange section is 1358 millimeter. It is slightly more than 1358, but we can safely remove this decimal part and we can consider 1358 as the effective width of the flange. Then our next step, we assume that the neutral axis is in flange. That means XU is less than the depth of flange. Then first we find out the location of the neutral axis with this assumption. For that we balance C with T, and by now you know this expression, I don't need to explain. So what we get is XU as 171.75. Obviously this is more than the depth of flange, so our assumption is wrong. So we have to modify our calculations for XU estimation. So we cannot use this expression because a part of the wave, is taking part in bending. So for that, what we do, we now assume that the second case, XU obviously is greater than DF and DF is less than 3/7 XU. If that is the case, then again we balance C with T, and then we ultimately find out the depth XU, which is here. Of course, all of you can follow these two steps. We have derived this expression just a few minutes back. So what we get, XU is 116.19 millimeter. Obviously, this is less than 150. So this assumption is again wrong. Then we modify our assumption. XU is greater than DF and DF is also greater than 3/7 XU. We repeat the same exercise. We balance C with T and then we use these two expressions. And then finally, what we do, we evaluate XU, which is 209.25. And this is more than DF, right? And we also find out 3/7 XU, which is 89.68 millimeter, which is less than DF. So this assumption is correct. Now for this assumption, our first task is to find out, if you recall, YF using the expression which is already provided to you, that is the effective rectangular section. So we find out what is YF. Then our remaining task is to find out MR, which has two components, MR1 and MR2. So first part, again, this is very familiar to us. It comes from the singly reinforced beam, and then the additional part is the effective width with this rectangular section with depth YF, right? If you just quickly revisit the figure here, okay? So we have this rectangular part. Ideally speaking, we should consider this geometry, but that we modify using this YF, and we have now a rectangular section. So we can find out the effective width, which is BF minus BW divided by 2. So that multiplied by YF is the area. So yeah, we have twice of that area acting in the compression zone to offer this compressive force of C2. So that's what we do here. And then effectively we find out the moment of resistance of this section, which again I believe you can follow. We just put the values of FCK, XU, BW and all other parameters. Ultimately what we get is the moment of resistance, which is 1320.77 kilonewton meter. So that is the moment of resistance offered by this section. And from this example, you can see how systematically we can find out the sectional capacity. Now, as we do always, if we summarize this design methodology in steps and see how it goes for the design of flange section, you can see what is there on your screen. So we start with a known section size. Our task is to find out AST. Then step 1, again what we do, we find out the demand that comes from the load and appropriate factor. So with these we find out what is the demand, and then our actual design starts from step 2. First we calculate XU limit. Then based on the position of neutral axis with respect to flange thickness, we evaluate this. Once that is done, we first check whether the applied bending moment is less than this limiting value. If this is less than, obviously this MU limit, which is based on a simple rectangular singly reinforced beam and under reinforced condition, we can complete the design here only. But that is not the case. That we have already discussed in our previous lectures. We'll have this model only when we have BMU is more than MU limit. That is, a singly reinforced section alone cannot meet the demand, and therefore we need this doubly reinforced section and the special geometry to cater the need. Then in step 4, what we do, we assume XU equal to DF and then calculate what is MR or MR1. That is the moment of resistance from the compression side. We can also find out the moment of resistance from the tension side. That I am not going to explain now. Now in the step 5, if BMU is less than MR1, then what happens? Obviously, this condition is satisfied And for this condition, we can find out what is AST. You are familiar with this expression. This is as good as a singly reinforced section. We only take this full area of the flange part, and then we also consider the steel in the tensile zone and then calculate the amount of steel required to balance this external moment. Now, if this applied bending moment is in between MR1 and MU limit, then we assume this condition and calculate MR2. So, moment of resistance from the compression side, what we get is effectively this one. We have considered two different cases based on the location of the neutral axis in the web, and accordingly we can actually figure out what is the respective moment of resistance. So then finally we have this situation where we have if BMU, that is the applied bending moment, is less than MR1 and we have this condition satisfied, then we find out MR1, that is enough to balance the externally applied bending moment. If not, we have case 2 where these conditions are satisfied, then we go for this additional MR2 which is here. If not, we have the last case where the condition is given here, and accordingly we can find out what is the effective moment of resistance. Now, first we find out exact location of the neutral axis. Based on that, we calculate AST. Right. Now, we have two things to look into. One is XU. It may be greater than DF. Then if that is the case, we have to consider DF. If this is less than 3/7 XU, then we have one case. And then if it is more than 3/7 XU, and then we have another case. And then finally, once we find out AST, then we have to also satisfy the minimum and maximum limit criteria. And all of you are familiar with these conditions. So we check whether this condition is satisfied as per the respective codal clause. And of course, we cannot go beyond 4%. That limit also check. So once these limits are checked, all the design criteria is satisfied. Then we identify what are the diameter of the bar that we are going to provide to meet this AST requirement, and then accordingly we produce the sectional details. So let us take an example. In this example, we have to design a section for a factored bending moment of 650 kilonewton meter. The section is simply supported with L effective as 7 meter, as you can see here. So once we know L effective and it is simply supported, we can find out effective flange width, and for this problem we have the effective flange width as 1207 millimeter. Although B here is 1500, but obviously we will not get the full B, but a B effective which is less than that, and this distance is 1207. So now we already have factored bending moment which is 650 kilonewton meter, and then in the next step what we do, first we calculate XU limit. For XU limit we already know for the given material properties. For this case it is 0.48D and which is 312 millimeter. So now we have the limiting value of XU. So 3/7 of XU limit is 113.71 millimeter. Now XU limit is greater than DF because the depth of flange for this problem is 100 millimeter and DF is less than 3/7 XU limit. So here in case 1, then for case 1 we can find out the sectional capacity that will come from the two components C1 and C2, and once we put all these values we get this sectional capacity which is 902.1 kilonewton meter. Now the applied bending moment is how much? If we go back, we have 650 kilonewton meter is the applied bending moment. So this applied bending moment is actually less than this MU limit. So a singly reinforced section is designed. So what we assume, XU equal to DF equal to 100 and then calculate MR1. Okay. And then this is the value of MR1. Now, what we have, this BMU, that is 650, which is 650 here, is less than the MU limit that we have calculated 902. So this is 902. And then MR1 we have 528. Therefore, we have this condition, XU, we get it from this value. And then for case 1, we calculate what is MR2 and we effectively get MR2 as 806 kilonewton meter. Now, for this exact position of the neutral axis, for case 2, we have this condition. And then what we do, we balance this applied bending moment with this condition. And then we first find out what is XU. This XU is greater than DF. And then we find out 3/7 of XU. So which is less than DF, right? 3/7 of XU is 66.54 millimeter. So if that is the case, obviously, we can find out what is AST just by equating C with T, and then AST required, we can find out which is 3014.5 millimeter square. So that completes the design for this problem. Now, there can be a different situation where instead of a flange section, we have this type of section. Effectively, what we can do, we have here one web here, another web there. So we can combine them here and then we can convert them, this box section, into effectively an I section. That is the only modification. And once we do that, we can find out B effective. We know what is D effective. Then we can calculate what is this D. And then we already know BW. So we can follow the design steps as we have already identified. First, we find out XU limit. Then we check the location and the limiting moment capacity for a balanced singly reinforced section. If that is sufficient enough, fine. Otherwise, we have to follow the procedures depending upon the location of the neutral axis. It may be within the web, but within that 3/7 XU limit, or otherwise we have to take a part of that parabolic stress profile. So accordingly, we find out that those conditions, and finally we find out what is the sectional capacity, and then we can also find out what is the amount of steel required. So that completes the design for this problem also. You can see some of the examples here where we have these type of flange beams. As you can see here, a part of this section of the slab will take part in bending with this beam here. So it is basically a flange section. And first we have to find out what is this effective width of this beam, and then we can design it accordingly. You can see the formwork here, and the point to be noted, what I told you at the first slide, is that if we have a situation where this web is not monolithically constructed with the web, then obviously we cannot apply that theory. For monolithic casting, what we have, rebars going through out the web. As you can see here, we have these bars, and this entire thing, actually it's a part of that beam coming out up to that top level of the slab, and that's how a part of the slab will take part in bending because of this monolithic casting. So with that, let us close here. You have seen how we can also consider different geometries. For example, you have T, L, or we have box or inverted T or L, or many other types. We can use the same stress profile, but the only point to be noted here in the design of this kind of flange section is the effective width of the flange and the location of the neutral axis. If the neutral axis is well within that flange part, then the entire thing behaves as good as a rectangular section, and we can design that as a singly reinforced rectangular section. Or otherwise, if the neutral axis is within the web, then first we have to find out its exact location, and based on that exact location, we have to find out the sectional capacity. So go through these derivations and the examples. If you have any doubt, do let us know, and then we will clear your doubts as you raise your questions. Thank you very much.